Hi, welcome back to physics. Today we're going to be talking about vertical kinematics, and as you can see before you, I've written down the 4 kinematics equations that we used the other day. And today we're going to use these same equations, except instead of working in the horizontal direction, we're going to work in the vertical direction. And so we use the same equations that you can see here. The same rules still apply. The main difference on the equations is that when you see a delta x, you make it a delta y. That's really the only difference that you're going to see in any of these equations. So this would be delta y equals 1/2 v plus v naught. This would be delta y equals v naught t plus 1/2 at squared. And this would be v squared equals v naught squared plus 2a delta y. So let's talk about some other things that we know here. Now, when we work in the vertical direction, there are some things that we just know right off the bat. And let's take the example of a ball that I throw up in the air. So here's the ball, it goes up in the air, it comes to a stop, and it comes back down. Now, I'm going to throw it up with some velocity. And because the velocity is going up, we're going to say that's positive. We choose up to be our positive direction. Now, as it goes up, we know that it slows down. So we know that something must be slowing it down, and we know that that's a force of gravity that's doing that. And if there's a force acting on an object, there is an acceleration. And we know that the force of acceleration due to gravity is negative 9.8 meters per second squared. Why is it negative? It's negative because acceleration is downward. Now, as the ball gets to the top of its path, it slows down so much that at the very top, it reaches zero velocity. So that's one thing we know. We know velocity at the top of the path is 0. It's just for an instant and it starts to fall again. It gains speed because it's now working together with that same downward acceleration of negative 9.8 meters per second squared. And eventually it's going to reach some final velocity at the bottom. Now at the bottom, that final velocity has the same magnitude as the velocity that you threw the ball up with, assuming that we discount air resistance. It's just got the opposite sign because its direction is downward. And this is only if it lands at the same level from which it was thrown. If the levels are different, if it falls further or if it doesn't fall quite as far, then that won't be true. Over here, we have displacement. So how high did the ball go? We refer to that as delta y. That's the displacement in the y direction. And if we're measuring from where we started to the top, that's going to be a positive delta y. But if we want to measure from the top to the bottom, that's going to be a negative delta y because that displacement is going downward. If we throw the ball up and it lands at the same level that it started at, then we know that the delta y, the displacement, is 0. It's kind of like if you run around a circular track and you end up where you started, you have no displacement. Well, the same is true here. If we start at ground level, throw it up, and it comes back down to ground level, the displacement is 0. So that is useful information for some of the problems that we do. Now, one more example here. This is an object falling off a cliff. So if you drop a ball off a cliff and you're not throwing it down, you're just letting go, the initial velocity of the ball is going to be 0. So you won't be told that in a problem. You just have to know that. The displacement of the ball going down, again, is going to be negative delta y because it's got a downward displacement. The velocity is going to be negative the whole time because it's going down, and the acceleration, again, is going to be negative 9.8 meters per second squared. So in the problems that we did that were horizontal problems, we were told an acceleration or we were finding some acceleration. But for vertical problems, we always know that the acceleration is negative 9.8 meters per second squared as long as we're on Earth. Okay, so let's do a couple examples. All right, and let's start with this problem. Okay, you throw a ball up in the air at a velocity of 10 meters per second. How high will the ball go when it reaches the top of its path? So, again, this is a kinematics problem, and I start out with a chart. So I've got V, V naught, A, delta y, and t. And I'm going to fill in everything I know before I pick my equation. Okay, so I know that I threw it with an initial velocity of 10 meters per second, and I know that when it reaches the top of its path, it has a velocity of 0. Again, up here it's going to be changing direction. The acceleration is constant, and it's a constant 9.8 meters per second squared, negative 9.8 meters per second squared. And I want to know how high is that ball going to go. So that's my question mark. So I look at the variables that I have and the one I'm looking for, and then I look at my chart, and the one that has those 4 things in it is equation number 4. So I'm going to write that down. V squared equals V naught squared plus 2a delta y. I'm going to put a delta y in instead of delta x this time. I want to solve for delta y. First of all, v is 0, so v squared is 0, so that's going to cancel out and just be 0. I want to get delta y by itself, so I'm going to move v naught squared over to the other side. So this becomes negative v naught squared equals 2a delta y. And delta y is being multiplied by 2a, so I'm going to divide both sides by 2a. And now I'll just rewrite it so it's neater. Delta y equals negative v naught squared over 2a. And I can plug and chug. So I go negative 10 meters per second squared. That negative sign is a function of me moving the v naught squared over to the other side. The answer to that will be a negative number. I'm not taking a negative 10 and squaring that and making it a positive 100. The answer will be negative. I divide that by 2 times negative 9.8 meters per second squared. So that's going to equal negative 100 meters squared per second squared over negative 19.6 meters per second squared. Well, my second squared will cancel out the second squared there. Meters will cancel out the square on the meter. And now I can just take my calculator. I'm going to take negative 100 divided by negative 19.6, and I'm going to get 5.1 meters for my displacement going upward. So that's how high the ball goes if I throw it with a 10 meter per second initial velocity. Now let's answer a follow-up question here. How long will that ball be in the air from when it's released to when it hits the ground? Okay, so let's make another chart. V, V naught, A, delta y, and T. And now, I know my initial velocity is still 10, but I also know the final velocity. The final velocity up here is going to be the same as the initial velocity, just in the opposite direction. So that's going to be a negative 10 meters per second. So that's going to be negative 10 meters per second. Acceleration, again, I know is negative 9.8 meters per second squared. And I also know the displacement now because it went up and came back down to the same place, so there is no net displacement. So we want to know what is the time. So I look at that and I go, well, I could use any of my 4 equations because I have every variable except for t. Actually, I can't use an equation that doesn't have t in it. So I need an equation with t, but that gives me the first 3 to be available. So I'm going to use the first equation. V equals V naught plus a t. And I'm going to solve for t. So I'm going to bring V naught over to this side. So now I've got V minus V naught equals a t. T is being multiplied by a, so I'm going to divide both sides by a. Cancel out a. And I get t equals V minus V naught over a. So plug the numbers in. V is negative 10 meters per second minus V naught, which is 10, divided by negative 9.8 meters per second squared. Negative 10 minus 10 is negative 20 meters per second, divided by negative 9.8 meters per second squared. And get out the trusty calculator again, and we go negative 20 divided by negative 9.8 equals 2.04. So I'll just round that to 2.0, and that is going to be in seconds. So that's my time. Now let's do another example. This time, let's drop a ball off a cliff, or off a building, rather. We know the building is 49 meters tall. What is the final velocity of the ball? So again, start out making your chart. V, V naught, A, delta Y, and T. Delta Y in this case is the height of the building, but it's negative because the ball is going downward, so it's negative 49 meters. A is still negative 9.8. V naught, I'm dropping the ball, so it starts with 0 velocity, and I'm looking for the final velocity here. So I look at my chart, I've got the first 4 variables. That means I'm going to use equation number 4. So V squared equals V naught squared plus 2A delta Y. I'm going to solve for V, so I don't have to do any real rearranging here, but I will have to take the square root of both sides to get just V. So I take the square root here, and then the square root of this whole thing. So V equals the square root of V naught squared plus 2A delta Y. So plug your numbers in, and you get the square root of 0 plus 2 times negative 9.8 times negative 49. And let's get the calculator out for that one. So 2 times negative 9.8 times negative 49 equals 960.4, and if I take the square root of that, second square root, second answer, I get 30.99. I'll round that to 31, and that's in meters per second. Now that, we have to do one more check. The ball is moving down. So that means it has to be a negative velocity. So I can, use my knowledge of physics to add this negative sign right here, but I can also use my knowledge of math. Whenever you take the square root of a number, you are given the plus and minus root. And again, using your knowledge of physics, you have to pick the negative root in this case because of its downward direction. That negative sign needs to indicate which way it's going. So that's our final answer. Now one more follow-up question. How long will it take for the ball to hit the ground? Okay, so let's again make our chart V, V naught, A, delta X, delta Y, and T. And so A is negative 9.8 meters per second squared, delta Y is negative 49 meters, and V naught is 0, and we want to solve for time. Okay, so I look at my equations, and the variables that I have tell me that I need to use equation number 3, which is delta Y equals V naught T plus 1/2 AT squared. So V naught is 0, so that whole term cancels out. So I'm left with delta Y equals 1/2 AT squared. I want to get T by itself, so I'm going to multiply both sides by 2 to get rid of the 2 here. And then I'm going to divide both sides by A to get rid of that A. And let me rewrite. So I've got T squared equals 2 delta y over a. Now I want t not t squared, so I take the square root of both sides. And so now I've got, move it up here, t equals the square root of 2 delta y over a. Plug your numbers in, and you get 2 times negative 49 over negative 9.8. So let's get the calculator out, and I go 2 times negative 49 equals negative 98 divided by negative 9.8, and I get 10. And now I need to take the square root of that, second square root, second answer, and I get 3.16 seconds. So some of you, and actually let me round that to 3.2. Now some of you might say, well, how do you know not to take the negative root of that one? Well, it's time. We can't have a negative time. Time is a scalar quantity. So that is how to do problems with vertical kinematics and kind of employing the things that you know. A lot of these problems will not specifically tell you some of the information that you should already know. So for example, when I dropped this off the cliff, I never said initial velocity was 0. The fact that I dropped it was telling you that it was 0. The acceleration is negative 9.8. I didn't tell you that in the problem, but it's gravity that's at work here. So unless there's a jetpack on that ball pushing it downward, it's falling with free fall, so that's negative 9.8. By the same token, on the other problem that we did before, you were not told specifically what the final velocity of the ball was, but just knowing that it reaches the same speed that it was thrown with is something that, again, you need to understand from the problem. A is negative 9.8 in both cases again. Delta y on the bottom problem was 0 because it landed at the same place from where it was thrown. All right, that's it.